So this problem says, in a study of waters near power plants that release wastewater into the water system, it's found that 5% showed signs of chemical and thermal pollution, 40% showed signs of chemical pollution, and 35% showed signs of thermal pollution. So chemical pollution is, it's chemicals getting in there. Thermal pollution means it's, extra heat is being released, and that's not good for fish and that kind of thing. Assume the results of the study accurately reflect the general situation. So they're doing a study, and effectively what this sentence is saying is, based on the study, we can take these numbers to represent probabilities. That's what they really mean by saying it. It reflects the general situation. First question. What is the probability that the stream that shows some thermal pollution will also show signs of chemical pollution? And there's a similar kind of question next. Let's focus on this one as well. Okay, so this does also involve a new concept here. What do we have? So we're taking a stream and making some measurements, and we're assuming we know based on our measurements that this stream shows some signs of thermal pollution. It's warmer than it should be, for example. Based on that knowledge, what is the probability that we're also going to see signs of chemical pollution if we do a different kind of test for chemicals that we'll see some sort of chemical pollution? Okay. Let's conceptualize this before we answer it with a Venn diagram. What does the box for the sample space represent here? You could think of it as representing all streams near all power plants, or every stream that is near a power plant. What, in just one state? Well, not necessarily. Maybe you think it applies to every state in the country, or maybe every country in the world. Do you have to specify what kind of power plant it is? Maybe, but we're not worrying about that. Okay, so you could think of this sample space, an element of the sample space, effectively being representing these different streams. And the characteristics of the streams about whether they show chemical or thermal pollution. Does that mean you need to use a bunch of C's and T's? Well, they could be sort of tags in your mind or in a spreadsheet for any given stream. But we don't have to be that fancy about it. We can just say, okay, if 40% show signs of chemical pollution, we can think of that blob as being the event that it shows chemical pollution, which I'll go ahead and denote by a C. And P of C is 0.4. Okay, we don't have to be super fancy about saying exactly what the sample space is. I specified in a way you could think of it, but you don't literally have to write it down. Okay, we're just trying to solve the problem. Another blob would be the event that it shows signs of thermal pollution. 35% shows signs of thermal pollution. Where should I draw the blob for thermal pollution? Well, because 5% show signs of both, there should be some overlap. Since it's 35%, should I make it a little bit smaller of a blob? Well, you can. I guess maybe I made it a tiny bit smaller, but it's hard to tell. That blob represents the event that there's thermal pollution in a randomly chosen stream, and its probability is 0.35. 5% of streams show signs of both. The probability of C and T, use the intersection symbol for and, is 0.05. And you might say I did draw it so that shaded blue region is about 5% of the total area. But again, you don't have to try to draw it accurately that way. The areas are just supposed to be suggestive. They don't have to be drawn completely accurately. So if you're asked, we're not asked this kind of question, but if you were asked the following kind of question, you could pretty easily answer these kinds of questions. You could say, what is the probability that a randomly chosen stream does not show signs of chemical pollution? Well, that would be 1 minus 0.4, 0.6. That would be using not an axiom, but property 5, which we proved. That was the one we did the sketch of the proof of. What's the probability that it does not show signs of thermal pollution? It would be 1 minus 0.35, 0.65. Again, that's not what we're being asked in the question in the PowerPoint slide, but it is a question you could be asked. You could also answer, what is the probability that it shows signs of chemical or thermal pollution? C union T. Again, we're not asked this, but you could be. Well, we need the general addition rule, which was property number 6. So these would be examples of basic kinds of problems that you could be asked, though technically you're not asked in that PowerPoint problem that I was highlighting. And this would be 0.7. So what is the PowerPoint problem highlighting? You should be able to do these. You should also be able to do what we see. There's probably one more problem I should ask before we look at that. I should ask, what's the probability of the complement of C union T? That's not cut, it's C union T. That would be 1 minus the probability of C union T. That would be 1 minus 0.7 is 0.3. But this is worth bringing up for another reason, because the complement of C union T turns out to be the complement of C intersect the complement of T. And what does that mean in real life for this problem? To be in this set means you are in C prime and you're also in T prime. You're in the complement of C, you're also in the complement of T, meaning your stream doesn't show signs of chemical pollution and also does not show signs of thermal pollution. So this would be the answer to the probability that a randomly chosen stream does not show signs of either kinds of pollution. This is worth bringing up as another kind of problem you might encounter. The fact that these two things are equal has a name. It's called a De Morgan law, the equality between these. This is a De Morgan law after somebody named De Morgan. That's a sideways equal sign there. It's not an 11. That's not an 11. It's a sideways equal sign. The intersection of the complements of two sets is the complement of the union. That's what it says. You can also switch around the roles of the union and intersection, and you get another De Morgan law. Coming back to the problem at hand, though, what is the probability that the stream, if the stream shows some thermal pollution, if we know it's in T, what are the chances it's also in C? That's called a conditional probability. The conditional probability is tricky, but very important. We know it's got thermal pollution. What are the chances that it also has chemical pollution? That conditional probability, notation-wise, is written like this. What is the probability of C given that T has occurred? This symbol represents the conditional probability of the first event that you see, C, given that we know T has occurred. And I think I might have spelled occurred wrong. It's just one R. I'm not remembering. Occurred might be just one R. I think it is two C's. that vertical line is sort of shorthand for given that. You know, in set builder notation, the vertical lines mean such that, or with the property that. Here in conditional probability notation, it means given that. It's always the probability of the first thing, given that the second thing has been known to occur. And that's what we're trying to answer here. We're trying to find that conditional probability because we are pretending we know that the stream has thermal pollution. It shows signs, and we're taking that to mean, yes, it does have thermal pollution. We want to know the chances it also shows signs of chemical pollution. In the Venn diagram, it's as if you're saying we're in the red blob for sure. We know that thermal pollution has occurred. What are the chances now that chemical pollution has also occurred? If you're thinking of the probabilities as areas, as a convenient way of conceptualizing it, I hope it makes a little intuitive sense that the probability that we're after, if we know we're inside the red blob, and we want to find the probability now based on that knowledge that we're in the green blob as well, I hope it makes intuitive sense that you would take the area of what's shaded in blue there in the intersection and divide by the total area of the red blob. And that is what's done. Though when we write it as an equation, it's not literally areas, it's probabilities. It's the ratio of two probabilities. The probability of being in both blobs, C intersect T, that represents what's shaded blue there, divided by the probability of being in the red blob, P of T. So this is 0.05 divided by 0.35, which is 5/35 or 1/7, and that is about 14%, I believe. 0.1428, I think. I should know that. Yeah, 0.142857. I did. I just was feeling a little uncertain. About 0.14, say. Not the same as the probability of having chemical pollution overall. If you don't know anything about the thermal pollution, you look at a stream and say, what's the chances that this stream has chemical pollution? You say it's a 40% chance. If you happen to know it's got thermal pollution, it makes the probability of chemical pollution smaller. Does that make sense? I'm not saying it makes real life sense. I'm just saying that's what the answer would be based on these data. Based on the information we're given, this is what the answer would be. It would be a smaller probability. Evidently, if there's more thermal pollution, there's less chemical pollution for some reason in general for power plants. I'm not saying it matches real life. I'm just saying that would be what the answer is based on these data. The next question is, what is the probability that the stream showing chemical pollution will not show signs of thermal pollution? Not show signs of thermal pollution. We're given that it shows chemical pollution this time, unlike the previous question where we were given that it shows thermal pollution. We're given that it shows chemical pollution. In the second part, we want to find the probability that it does not show thermal pollution. Oh, tricky, tricky, tricky. These do get tricky. You got to write down the right symbol to help you make sure you get it right. The same idea holds, though. It's a conditional probability. We are given that it shows chemical pollution. We're assuming we're in the green blob. What are the chances that we're not in the red blob? But we're still in the green blob. It should be the area-wise, the proportion of this area in the green blob that's not shaded blue to the entire green blob, including the part that's shaded blue. This is the ratio of the probability of the intersection, C intersect T prime, divided by the probability of the entire green blob, which is P of C. Now, we never found that quantity right there anywhere. I never wrote that down. Probability of showing chemical pollution, but not thermal pollution. But we could pretty easily figure it out from the diagram. Being in C, but not T, means you're in this part right here. The entire area of the entire green blob is 0.4. The area of the blue shaded region is 0.05. Therefore, we've got 0.35 in there. Say it again. I said area, but I really meant probability. The area or probability of the entire green blob is the 0.4. The area or probability of this little shaded blue part is 0.05. Those have to add up because they're mutually exclusive, these two sets that I'm pointing at, to the entire probability for the entire green blob. Therefore, this has got to be 0.35 because 0.35 plus 0.05 is 0.4. This is 0.35 here, and the probability of C itself is 0.4. And that turns out to be 7/8, 0.875. By the way, that's a complementary event to this one. This is going to be 0.05 divided by 0.4, 1/8 or 0.125. These have to add up to 1. But they are conditional probabilities there. For our last 5 minutes, let's continue talking about conditional probabilities, but with maybe what you might think of as a simpler situation. You can get out your deck of cards if you like. You don't have to. Deck of cards, do it this way. Ace, 2 through 10, face cards, Jack, Queen, and King. 4 suits, clubs, diamonds, spades, clubs, hearts, spades, and diamonds. Clubs and spades are black, hearts and diamonds are red. 52 cards total, 13 in each suit. What's the random experiment? The random experiment is to take the 52 card deck and shuffle it well, and then pick one card at random, just one. You could try to answer questions like, what's the probability that it is a heart? Well, there's 13 hearts out of 52 cards, 13 50-seconds, which, yes, is 1/4. 0.25. What's the probability that it's the Queen of Hearts? I could write that as Q heart for Queen of Hearts, but realize if I do that, that it really does mean Queen and a heart. So it's an intersection. There's only one Queen of Hearts, 1 out of 52. A little less than 0.02. What's the probability that it's a queen or a heart? There we pretty much have to write a union symbol. Well, you could count up how many queens and how many hearts there are. There are the hearts, 13 across there. There are the queens right there. Oh, we'd be double counting the Queen of Hearts, though. So it's not 13 plus 4, it's 13 plus 4 minus 1. 16 out of 52. Or if you prefer, effectively the same thing is to use the general addition rule and subtract off the probability of the Queen of Hearts. Probability being a queen. It's good to keep denominators of 52 here. It's 4 out of 52, Probability of a heart is 13 out of 52. Probability of being the queen of hearts is 1 out of 52. They all have the same denominator. So yes, effectively you are taking 4 plus 13 minus 1 over 52. 16 over 52. That can be reduced to 4/13 if you like. And 4/13 is about 0.308. Or 0.31 if you prefer. About a 31% chance that if you randomly pick one card out of a well-shuffled 52 card deck, that it will be a queen or a heart, or both, the queen of hearts. And it's nice to think about conditional probability in this context as well. Take one card off at random. Don't look at it. Show it to your friend. And they say, hey, guess what? It's a red card. What's the conditional probability that it's a heart, given that it's a red card? Your friend has told you it's red. Now you're wondering, how does that affect the chance that it's a heart? It does affect it, right? You could think of this as, hey, there's 13 hearts out of 26 red cards. That's why the answer is 1/2. You could also think of it in terms of the formula we wrote down 5 minutes ago. It's the probability of being both a heart and red divided by the probability of being red. You're either a heart or a diamond here. Being a heart and red means you are a heart. That's 13 out of 52. Being red means you're a heart or a diamond. That's 26 out of 52. And yeah, the 52s cancel, giving us the same answer. Hang with me, give 30 more seconds. What's the other conditional probability? Where you switch them around, the probability of being a red card, given that it's a heart. Hey, that's 1. If you know it's a heart, it's for sure red. And these are not equal. You should not expect that if you switch around which probability you're finding and which event you're given, that you should get the same answer. And in this case, once again, this is different than the probability of getting a heart. This is different than getting the probability of red. These events, getting a heart and getting a red, are called dependent events. But there are some independent events, like getting a red and getting a queen, whose knowledge that it's a queen doesn't affect the chance that it's red. Those are called independent events, and it's a big topic for Thursday's class.